I'm going to present. Okay. I'm going to present my project about the 3-question guessing game that I did for the REU project. So the problem formulation is that there are 3 questions and each one can be answered by a yes or a no. A yes is denoted by 1 and a no by a 0. The correct answer can be represented by a 3-bit binary sequence, and there are 8 possible 3-bit sequences. So the purpose of the game is to find the correct 3-bit binary sequence and to search for the solution with the minimum steps to get the answer. After a guess is made, the feedback will tell the number of incorrect bits, but it will not tell where the errors are. The probability of guessing the correct 3-bit binary sequence in the first guess is 1/8 because to get the probability is 1 over all the possible binary sequence, which is the size of the set, and the size of the set initially is 8, so that's why it's 1/8. After doing a guess, the probability will increase because the size of the set will decrease, because each time that I do a guess, the set will divide into different subsets, and each subset will have a smaller size. So an acceptable solution for this problem will be one that tests all the possible guesses that could have been made. So it also tests the method for all the possible correct 3-bit binary sequence in order to know, even in the worst case, how many steps it will take to get the correct answer. And so each guess should do a balanced partition of the set, and also the next guess will depend on the feedback of the previous guess. So this is what the initially set will look like if I have 3 questions for this game. And after I do a guess, this set will be divided into 4 different subsets, because it is going to be built by the information that I get from the feedback. So each guess will compare bitwise the guess with each other of the possible answer of the current set. And it will divide the set in subsets according to how many bit errors it has. So the size of the set gets smaller after each guess, and the probability will increase because the set is going to decrease. And the probability will increase till it is 1 because the set is going to be finally of size 1 when I'll just have 1 possible binary sequence. So this is an example of how a guess divides a set. If I have these 3-bit binary sequence, and after I do a guess of 000, if I do a bitwise comparison with each one of that space, I'll get, if my feedback is 0, my subset will be, one of my subset will be a binary sequence of 000, and if my feedback is 2, I'll know that my subset is going to have size 2, and we'll have 3-bit binary sequence. So as I said before, there are 4 options of feedbacks ranging from 0 to 3 because I have 3 questions. If I have 5 questions, I'll have my feedback can range from 0 to 5. Also, not always each possible feedback will have a subset itself. As in the example before, I just my possible feedback was going to be 0 or 2. So if my size of subsets is 1, the binary sequence is the answer. And if it is bigger than 1, another guess needs to be made to get the answer. So for the first guess, if I get the feedback 0, that's my answer. If it is 3, I just have to not the 3-bit binary sequence. But if it is 1 or 2, I have to do another guess until the size of my set is 1. So, but how do I choose what guess it's the best one to do my guess? So my first assumption is that any of the 8 3-bit binary sequence can be used as the next guess. But so I take each one of them and do a bitwise comparison with the current set and compare the subset created with each different guess. The purpose of doing this is that I can see how balanced each guess partition the subset. So I'll took the guess that its maximum size of the subset is the minimum among the other guesses. This process will eliminate some possible 3-bit binary sequences as a guess, but others are going to still be considered good candidates because they are going to give the same balanced distribution. So if I don't know any more information about my correct answer, any of my candidates are going to be good enough to be a guess. But to get a complete solution, I have to test it for all these guesses. So I'm going to have different solutions. So I can compare them, all of them, and see which one of them give the best solution. And the best solution is considered one that the minimum steps that has the minimum steps to get the answer even in the worst case. An example to choose a guess is if the current set is 30 and my option guess 1 will produce 3 subsets of 10 3-bit binary sequence each one, and the other guess will produce 2 subsets of 15 3-bit binary sequence. I'll take the first option because it will give me a better distribution because its maximum size of the subsets is the minimum among the options. So my evaluation criteria to evaluate which solution is the best one is the maximum depth and the average depth. For this, I use a tree as a tool to evaluate its efficiency, and each branch represents a process by which the correct 3-bit binary sequence is guessed. So why I consider the maximum depth? Because by minimizing the maximum depth, the worst case will do the minimum steps as possible. And the average depth, because by knowing the average depth of a method, one can gain confidence on the method. So the lower maximum depth and lower average depth is going to give my optimal tree. So so it is going to be considered the best efficiency, the algorithm that takes into account the feedback in a way that each feedback divides the set into balanced subsets. So for the best efficiency, in the last time that I present this project, I said that it will be 2 because of how it distributed, but I need to test it by the computer. Not. So this is an example of a tree, of how it forms a tree. So at first I have 8 3-bit binary sequence, and after my first guess, it is going to divide the set into 4 subsets. So the subsets that are going to have a size of more than 1 is if my feedback is 1 or 2, and after that I have to do another guess, but it cannot be the same guess that I did before, because it will not divide the set into more subsets. It will remain the same. And so basically, here I have 8 lifts, which are the children, and this is how each one of the possible correct answer can be found. This is another example of how, if you choose different guesses, it can still give me the same structure of the tree. And when I say the same structure, I mean the same depth and the same average maximum depth. So, as a conclusion, there is more than one guessing sequence that can reach the minimum depth of the full tree construction. And before, I just showed 2 examples of how the same structure of the tree can be reached, but there are hundreds of them, because there are different guesses that can be made, but obviously each set will be different. The same methodology can be applied to any number of questions, but the complexity of the computational program will increase as n increase, because as n increase, the number of n-bit binary sequences increases exponentially, and the tree will be bigger, and millions of trees can be created as n gets bigger. So this is how an acceptable solution to n-question games can be reached. First, you get the set of 2 to the n-bit binary sequence. Assume that all of them has equal probability of being the right one. Get the best candidate to do a guess by choosing the ones that produce a balanced distribution of the set. Get a tree with each one of them. Do the same in each level. That is, compare with different guesses how efficient it is. The trees with the lowest depth and lowest average depths are going to be the optimal trees. And that's it. Any questions?
So I guess you started with like 10 question guessing game and then reduced to consider maybe 3-bit guessing sequence. Do you see substantial difficulty extending from, let's say, 3 to 10 to n? Like, what are the major difficulties in constructing a good method?
When I had the 10 question game, it was difficult to evaluate all the possible 10-bit binary sequences because there were 1,024 combinations, but here that I just had eight possible 3-bit binary sequence, it was easier to see how it works and how it has more than one solution, and to really see how efficient it is. There is a need to see all the possible answers. With 10 question games, it was difficult to see that.
All right, so now with the study on 3-bit guessing game, do you see any possible way of extending that to n question guessing game? Because it seems that you say you can extend, it's just computationally it requires a lot of enumeration, but do you see any particular way of constructing a good guessing sequences?
Yes, I think that evaluation criteria should be the same. The best solution will be the one with a maximum depth, and where the average depth will be the minimum too. And besides that, the method to solve that, I think the condition to divide the set in a balanced way should remain the same, because it doesn't matter how huge the set is. It should always partition it. The guest should always partition it in a balanced subset.
Well, I think last thing I want to ask is whether you have any perspective in how this can be used for a guessing game of longer sequence, in terms of, like, for instance, I would say whether you have a concrete method to solve this problem, or maybe you just say, I know what would be the best, like the lower limit on the number of guesses needed to find a solution for n question guessing game. Do you have any kind of like upper lower limit on, like, what would you expect on the optimal method of constructing the full tree?
I think that the upper limit will vary depending on the n, on the number of questions, and so I think that it should be analyzed particular to the number of questions that I have. I mean, the minimum will always, for the maximum depth, for 10 question guessing game, I got of 8 the last time with a method, but to better say that it's an efficient method, I think that all the possible options should be analyzed.
Okay, so maybe let me put it in another perspective. If you want to guess the correct bit sequence as early as you can, would you choose the sequence that has the largest probability, or you probably don't want to do that? You just say, well, I want to have a balanced partition, depending on the feedback. Which way do you prefer?
To have a balanced partition.
Why?
Because even in the worst case, it will reduce the steps to reach the answer. Because if it is not balanced and I just have a subset of size 1 and the other one of size 28. If my feedback will give me the subset of size 1, is going to be reached very fast, but if it's going to give me the other feedback, it will take more steps than needed. So if it is balanced, more or less all the possible answer is going to be reached in the same amount of steps.
Okay, and also I think another minor issue is that when you make argument, you say each step you want to have balanced partition. My question is it possible the first step you do have a balanced partition, but later the feedback becomes so non-meaningful, meaning that no matter what guess you make, you will not have balanced partition. Have you ever considered such kind of case?
For the first guess, all the possible binary sequence will give me the same kind of partition.
That's for 3-question guessing game, right? What I'm saying is when you extend to n-question guessing game, maybe you have similar observation. But is it possible later there are consequences on what partition would be better? Even if in the earlier stage for a particular subset you have a balanced partition, but later for the smaller subset you encounter substantial difficulty in creating balanced partition. Have you thought about that?
Yeah, but as n increase, I will have too many possible options for the guess, and it will be difficult to choose from one of them because it will not give me a really balanced partition. So that's why I thought that the only way to really know which one to choose besides how it divides the set is to test it with all of them.